Hey, this is Steven from RC Engineering, and welcome back to my Rule of Thumb series. Sorry, my voice is a little out. I was exhibiting at a event, so I was talking to a lot of people. My voice went out. All right, so this video is going to be pretty quick. I was finishing up my finals for this school semester, so I didn't have a chance to prepare one before. Just finished my last final today, so I wanted to do the video today as today's Monday, so I already missed my Monday morning release schedule that I usually make. So I want to do a quick video. This isn't exactly the basics of batteries, and I spelled battery wrong, but this is basically the practical knowledge of batteries. So not exactly the different types of batteries, but more of their specifications and how you could go off of their specifications to find out the battery that you want. And so here I have two settings from two different LiPo batteries from a company called Venom RC or Venom Batteries. And they make LiPo, nickel cadmium, or nickel metal hydride or nickel cadmium, and also li-feed batteries. So there's all those different types of batteries. In another video I'll go into those as well. LiPo, lithium ions, nickel metal hydrides, nickel cadmiums, Li-Fi, LiHV, etc. And into the pluses and minuses of those. But because I had limited time, I just threw this together to go into some of these things that not a lot of people really understand when they're going to buy batteries for any of the RC models that I'll be covering, for example, planes, cars, and boats. And so most of those that are all using electricity or electric motors are going to use batteries. Also, they'll have batteries to move servos and stuff like that, even for sailboats and stuff like that. All right, so first thing you're going to notice here is that battery type, and most batteries will have this type of specifications that tell you how they function. Not all of them will go into as much of a depth as this is going in. As you see, it has a whole bunch of specifications, but we'll go into that right now. So the battery type is a lithium polymer, otherwise known as a LiPo battery. And then we see the C rating, which we'll go over in a second, the volts, and the capacity. Now, first thing we're going to go over is the volts and what makes up the volts. So the voltage are basically how many of those cells are in parallel to get the voltage, right? Because each cell, so you have one cell, right? 1S. This is a 3S, so that means it's 3 cells. So for each different types of battery chemistry, they have their own nominal voltage level, right? So for these batteries, for LiPo batteries, their nominal voltage is 3.7 volts per cell. So if your motor or your ESC or whatever, or if you need a certain amount of power for a particular model, and let's say you need 12 volts. In order to get 12 volts, you have to string together these cells in what's called series. So you'll see here, this is what this S is, 3S. So what that is you take 3.7 plus 3.7 plus 3.7. And when you add all those together, so here this is 21 and 3, 6, 9, 1, 1, 1. And that's what you see here. The 1.1 volt nominal. And when you have the cells in series, the voltages add up. So each of these cells add up to be 11.1 volt. And that gives you 11.1 volts that you see here in the specifications. However, normally on different chemistries it's different, but for LiPos you generally don't want to go down that low per cell because you'll damage the cell. So they also have a maximum cell voltage, which you see here is a 4.2 volt per cell. So if we fully charge this battery, we have a 4.2 plus 4.2 plus 4.2. And so that's 4, 16, 20, 2, 4, 8. So 4, 6, 4, 8, 12. Yeah, so 4 times 3 is 12, and then 2 times 3 is 6. So a total fully charged voltage of 12.6 volts and a dead voltage of 11.1 volt. So that is what the different cells are. So if you're looking for an electric motor and it says, hey, we recommend using 2-cell, that means that you're looking for a 3.7 plus 3.7 is equal to 7.4 volts. 7.4 volt. And that 7.4 volt is equal to a 2-cell battery. And so on and so on. So you have 1-cell, 2-cell, 3-cell, 4-cell, 1-cell being 3.7. But normally it will only say the nominal voltage. It will not say the maximum voltage. So this is the nominal voltage, which is normally for a LiPo the lowest you want to take your battery to. Now for example, this max voltage per cell, there's also something called LIHV, which basically means that you could overcharge your cells. So their maximum voltage per cell is actually 4.35 volts. So that's why they're called LIHV, which are basically kind of like LiPos, but they are high voltage. Reason being is you could charge them an extra 150 millivolt. Okay, so yeah, so you see here max volt per pack, 12.6 volts. That's what we found over here. And then minimum volt per pack is 9 volts, but obviously if you get to 9 volts, you're really damaging the battery and it's not going to return. That will be in another video. Now, those a lot of you guys will know, but we'll also get into the C rating. That's also pretty abstract, and a lot of people don't know much about that. Now let's talk about the capacity. So the capacity is labeled on every single battery, regardless of the capacity, as well as the voltage, regardless of the capacity. Regardless of the chemistry. So the voltage per cell is regardless of chemistry. It's independent on chemistry, right? So each chemistry will have a different nominal voltage per cell, but capacity is the same regardless of chemistry when you're looking at the specifications. So here we have 1300 milliamp hour, and milli is in a metric unit, which means 10 to the negative 3. Otherwise known as, if you move the decimal place over 3 times, you get rid of this milli. So now we have a 1.3 amp hour. So 1300 milliamp hour means 1.3 amp hour. So if you had a calculator and you put 1300 and you multiplied it by 10 to the negative 3, or you divided it by 1,000, so 1300 divided by 1,000 is equal to 1.3 amp hour. So basically what that means is the maximum amperage that you could pull that will be stored in the battery. So let's say you have a motor, electric motor that pulls 5 amps. So we have 5 amps here. So we have 1.3 and we have 1.3 amps, so we're going to see what we're left with by canceling out units, right? This is called dimensional analysis in mathematics and engineering. So we cancel out this A with this A, and so now we're left with hours over unitless. So we're going to be left with hours. So basically what we're going to do is when we divide the 1.3 divided by 5, we're going to see that we get a 0.26 hour battery life. Obviously this is ideal. There's obviously more drain than just the motor. And also batteries could react differently according to the temperature outside and other factors. And also how much you charged it. If you don't charge it all the way, then you're obviously not going to get as much capacity. So this isn't ideal. So this is just when you're, running ideal calculations. So let's say that we want to turn this into how many minutes can we fly or drive or go around with a car or boat or whatever. Or boating. So fly, drive, or boat. So what we're going to do is there is 60 minutes per hour. And so hours cancel out, now we're left with minutes. So 0.26 times 60 is equal to a total of 15.6 minute runtime. So that's kind of what you're going to go off of, is how long do you want to drive, boat, or fly. Of course with flying it's a little different because you could get a too big of a battery and your plane doesn't even fly. Obviously, cars and boats, or with a boat, you could put too big of a battery in it, and there's not enough buoyancy in the plane, and the boat sinks. So that's how you figure out what milliamp hour you need or what capacity you need. And by changing it into, if you do not change it into amp hours, you will have problems when you do these calculations. So make sure you turn it back into amp hours and then figure out how many amps that your motor is going to pull by looking at your motor data sheet for your car, boat, or plane. And then divide the capacity by your amperage, and that will tell you how many hours. And then if you want to go from hours to minutes, take the hours and multiply it by 60 minutes per hour. Alright, so that's milliamp hour or capacity. Now let's go into C rating. So C rating is shown right here. This will also be shown quite a bit on a battery. A battery will show you, generally most batteries will show you C rating, nominal voltage, cell count, and capacity. So what is C rating? C rating has to do with how many amps that battery can discharge. What rate can that battery discharge at? So here we see that we have one battery at 75C and another battery down here at 50C. So the higher the C rating, the higher the discharge. So what exactly, with knowing the C rating, how can I tell if, let's say that it didn't have any of this other information, how could I tell the max discharge rate of this battery? So I could make sure that if I have a high-speed plane, boat, or car, and I need to draw a high amperage on my motors, how can I make sure that the battery could keep up and that I don't destroy the battery because it cannot keep up? So what you do is you take your C rating, which for this battery is 75C, and it's actually the amp draw is dependent on the capacity of the battery, mainly having to do with the C rating. The C rating is derived from the capacity of the battery. So what you do is you take 75 and you multiply it by the amp hour. So make sure you convert it from milliamp hour to amp hour. So for this one, we have a 1.3 amp hour. So 75 times 1.3. So this is the C multiplied by the capacity, multiplied by amp hour. And that will actually give you the continuous discharge. Normally this is the rating. If it has it on a battery, it's normally the continuous discharge. So you could continuously discharge this amount as long as you have adequate air around your battery. You could discharge this until the battery is dead, until you hit 11.1 volts or higher, depending on what you like to fly and how you like to keep your batteries. So 75 times 1.3 is equal to 97.5 amps. So you could continuously, from this particular battery with a 75C rating, you could pull 97.5 amps. And look what we got right here, continuous discharge. We got it right, 97.5 amps. But we see down here that our max burst rate, which generally they'll tell you the amount of time that you could do this for, if they say, 10 seconds or 15 seconds or whatever. So usually this would be used for something like takeoff for an RC plane, or maybe get up to speed on an RC car, etc., or get up to speed on an RC boat. You'll pull higher amperage than if you're just cruising. So this would be for those types of situations where you need the power early on. So let's go ahead and do the calculations for that. I'm just going to do it on the calculator. Actually, I'll show you guys. So we have 150C times 1.3 amp hour is equal to 195 amps. And check it out, we got it right here, 195 amps. So from that, let's just do a little bit of an extra calculation here. So let's say we have the 1.3 amp hour, and let's see how long the battery will last on its continuous discharge rate of 97.5 amps. We see now that we're going to end up with hours. 1.3 divided by 97.5 is equal to 0.0133 on forever. Hours, multiply that by 60 minutes, that's equals to 0.8 seconds. Sorry, 8 minutes. Now that's pretty small. How many seconds is that? We're going to multiply it again by 60 to get 60 seconds in a minute. That's 48 seconds. So obviously, this batteries have come a long way where you could discharge the entire battery safely, somewhat, as long as you have adequate cooling of your battery. You don't overheat the battery. You could somewhat safely discharge an entire 1.3 amp hour battery in 48 seconds. Now with that, let's see what it is for the 1.3 amp and the maximum discharge rate of 195 amps. Oops, this is amp hour, this is amps. So amp hour cancels out, right? 1.3 over 195 is equal to 0.0066. Multiply that by 60 minutes in an hour. That's 0.4. That's 0.4 of a minute times 60. That's 24 seconds. So that's the max discharge rate. You might be able to get that max discharge rate before the battery heats up and destroys itself. But yeah, it's pretty crazy to show how batteries have evolved over the years, especially lithium polymer, with the increase in grades of cells that are used to get very high output. And you'll also see here that the cell configuration here, this is only one parallel cell. So basically what that means is you could also add cells to your batteries in parallel to boost your amperage. Instead of boosting your voltage like it does here, if you add a second set of cells that were also just like this, a duplicate of the last set, now you have two cells in parallel. And those cells will actually double your amperage output. So let's say out of this one you could only get, let's say here we have this guy, which is 97.5 amp discharge. That is the only safe discharge rate we could get continuously out of this 75C grade of cells. However, if we add a second cell of batteries in parallel, it will actually double that amperage and get you 10, and then this is 4, 5, that's 8, 9, 195 amps. And then you could do this continuously safely because the amperage is being shared throughout all these batteries, so all these batteries aren't getting super hot individually. They're kind of they're bearing the load. They're sharing the load of that amperage. So you could get these guys a little bit hotter, at this amperage rating they'll be drawing the same heat. They'll heat up the same amount. So even with no cells in parallel, as it says, only one P, which I believe means that there's only this first set here at the top. There's just one cell in parallel, and that's pretty good for batteries nowadays. Back in the day, you definitely couldn't do that out of a cell. You'll burn it up. And of course, back in the day, we didn't have lipos. Now, the final thing that we see here is we have an actual recommended charge rate and also C rating, and a max approved charge rate and also a C rating. So again, same exact thing, 1.3 times amp hour times the C rating of 1 is equal to 1.3 amps, which is correct. And again, 1.3 times 5 is equals to 6.5 amps, which is also correct. So that's pretty much it. Not all of the companies will put this down here, but any sort of company that will put this down here, and let's say that they don't tell you this, because like all Venom packs will tell you their max discharge rating, but some other packs will only give you a C rating. So you have to be able to calculate that. If you don't have the data sheet, you got to be able to calculate that from the C rating and the capacity to figure out if you're going to blow it up with your car, plane, or boat with the particular motor selections you have in it. Then finally, the most important part is the plug that the battery uses. So make sure also that when you buy a battery, make sure that the plug on your ESC and your plug on your battery match up so that they can plug right into each other. Otherwise, you have to use an adapter or you have to solder on a new plug. So down here, let's take a look at a different battery. This one is a I guess you would say, a lower grade cell. So we only have 50C discharge rate and a max discharge rate of 100C compared to this guy of 150C and 75C. So basically, what that means is that the cells inside of this one are higher grade, so they have lower. They would have lower or higher internal resistance. Technically, I guess higher or lower internal resistance. It depends on how they're orientated in series or parallel. So they're just higher grade cells inside the battery pack that will allow for this higher C rating. So generally, for the higher C rating, you're going to pay more money because basically what happens is they build all these cells. They construct all these cells, and then ones that could do the 75C rating and pass their tests, those are the best ones, the 75 or 100 Cs. Those are the best ones out of the batch, and those get labeled 75 Cs or 100 C discharge rate. And the ones that don't quite live up to that, they get labeled as 50 Cs. So ones that have defects and stuff like that, you might have them. Those are actually the 50 Cs and the 25 Cs. But that's why the 75C and 100C are so rare, because out of a whole batch, there could not be very many that meet that stringent of quality standards to get that high of a C rating. And that's pretty much it. Almost the same thing there for that guy. So if you want to pause the video, you could practice on that guy and see if you get the same answers that are labeled inside the specs. And yeah, that's pretty much it for this video. This is just the basics on figuring out how to do these calculations for the specification sheets for different batteries. So this is generally regardless of chemistry. Lithium ion's the same, LiPo's the same, LiHV's the same, LiFe's the same, nickel cad's the same, nickel metal hydride's the same. Everything's the same as what you see here. So you would be able to calculate pretty much any chemistry with this knowledge if they didn't provide you the answers to those questions. Or if you're out at the field, don't have any internet, let's say, you could take a look at your battery if it didn't have the answers on the battery and be able to calculate these specifications. Alright, so it's been Steven from RC Engineering. I'd like to thank you guys for watching this video on my Rule of Thumb series. Please subscribe for more videos like it in this series and also my other series as well. And I'll see you guys in the next video. Thanks for watching. Take it easy. Peace.